Hey everyone, so today I'm going to be covering the topic of discriminative random fields, also known as conditional random fields for image analysis. And the main reference of this presentation is basically a paper called Discriminative Random Fields. So before I do that, I'm going to talk about the intuition behind it. We're going to talk about some interactions of spatial interactions in images and discriminative versus generative models. Then we'll derive a conditional random field from Markov random fields, and we'll talk a little bit about the model itself and what it means. So just to give everyone a overview of a definition of a discriminative random field. You don't have to memorize it, but you just keep in mind as we go on with the presentation. So a discriminative random field is an application of a conditional random field defined over a 2D lattice. It's a discriminative framework for modeling posterior distributions directly as a Gibbs random field, and it implements a probabilistic discriminative classifier to define its Clique potentials. So there's two main contributions that the paper that I discussed earlier made, and it's basically the fact that they use a conditional random field over a 2D lattice instead of a 1D sequence, which is pretty much the original purpose of conditional random fields and Markov random fields as well. And then, and basically, the conditional random field is a better method that captures interactions between the data observation that are simplified or approximated when using a Markov random field. So before we get too much into the details, I want to talk a little bit about the intuition behind it. So we'll talk about probabilistic models and some interactions, the nature of spatial image interactions. So going way back, we'll talk about computer vision problems, so mainly low-level ones. Most problems in computer vision can be broken down into the task of assigning labels to regions of an image. And when I say regions, I mean stuff like pixels. It could be a superpixel. It could be a patch in an image. It could be irregular regions. And I represent it here by the square box. But just keep in mind, you could define a region in many different ways. And basically, we take a probabilistic modeling approach for this labeling task. And that process is called inference, which we're trying to find the most probable outcome with respect to some sort of cost function. And if you know anything about Bayes' theorem, we represent this as the posterior probability distribution. So it's the probability distribution of the parameters given the data. And basically, as we're trying to analyze images, we need to consider a few things such as spatial interactions within the images. You need to make some sort of assumptions behind it, and you can even make the assumption that there's no spatial interaction at all. Each pixel is independent of the neighbors, and you could use models like naive Bayes to do the inference process. But if we want to have a more in-depth understanding of these interactions, there are some things that we should consider, especially when we're trying to find the underlying process in the data that gave rise to continuous label values that describe depth in this case, this example that I gave here. So on the left side, you have the original image, that's the data source, captured by a camera sensor. And then on the right side, you have the label set. So this is what we're trying to find. And as I mentioned, it's a continuous data set, continuous labels. So instead of saying two different classes, Like this is a head, this is a lamp. We're trying to infer the depth, so it could take on any real value. So it could be a depth of 1 meter, 2 meter, 2.5 meters, stuff like that. So that's what I mean by continuous. And so there are two main questions I want you to consider as we go through the presentation. Is there any relationship between the label of a given site or region and their neighboring pixels? So when I say the labels, if I look at this, what we're trying to find, is there interaction? Is there any meaningful relationship between uh, the pixels on the right versus the pixels below it? And then the second one is, what about the spatial interactions about the observation data of a site and its neighbors? So now we're looking here. Are there anything we can distinguish when we look to the right and left? Are there colors, maybe some textures that can help understand the relationship between the original site that we're looking at? So basically, we can use graphical models to give us a probabilistic framework for representing these spatial interactions, and we can represent and manipulate global probability distributions like the prior term um, or the posterior term, stuff like that. So the graphical models give us a nice framework for doing this. So as we move forward, let's define some terms. So let's define a graph by S, which is the set of sites, which could be the pixels, regions, stuff like that. It's basically the vertices, and E is the edges. So edges are basically the interactions between the two sites. Here we're going to use X as the set of labels that correspond to the site. We call that a configuration. And then we're going to call Y the observed data, so the input data. So this might be a little backwards from how you normally think of things. Y is actually the input and X is the output. But just remember, X is the labels, Y is the observed data that correspond to the site I. And here we can represent this visually, what a random field looks like. So you have the nodes here. These are the sites. X again is the labels. Y is the original data, and you could see here that's kind of what it would look like. So this is the label set, and this is the original input data. Here you could see the interactions between the different nodes and sites. So V1, we call that the unary clique potential. It's basically the interactions of this of the individual site, and it could be described as a likely term, y given x, and it describes the distribution of a random variable x. V2 is the pairwise clique potentials, so this describes the interactions between two different sites. So it's kind of, think of it as like a push-pull relationships. You're basically describing the relationships through these clique potentials. So I want to talk about generative and discriminative models, but before I do that, I want to quickly introduce the Markov random field. I'm assuming that most of you already know Markov random fields, since we're covering the topic of conditional random fields. But basically, with the Markov random field, you're trying to describe the P of X, which is the set of configurations, as I mentioned earlier, of each site. So you're trying to find the probability distribution for each of the labels at each site. And we describe it as a Markov random field if it follows this property here. So the label of a given site is described by its global the labels of a given site described by it given its global interactions labels, and then the is equal to the label of a certain site given its neighbors. So we're basically saying that the local interactions can describe the global interactions. And we're saying that there's conditional independence given its neighborhoods. So one label given its neighborhood is um, equal to the probability distribution of another label given its neighborhood. So it's conditionally independent, and we can describe that as a product. Here's another thing, but this is implied, so it needs to be positive. And then using the Hammersley-Clifford theorem, you can describe a Markov random field as a Gibbs distribution. And then here is where we can break it down into the Clique potentials. So now let's move on and talk about generative versus discriminative models, as I'll come back to Markov random fields. So we can describe a generative model as that is a model that learns the joint probability distribution between the input features and the output classes. So here you get like a set of data, and you can generate a model that'll describe the data, and then you can make an inference between whether it's a class A or class B. So this is a discrete one, so we're labeling it as either label A or either label B. A discriminative model learns the conditional probability distribution of the output classes given the input features. So basically, a discriminative model defines the boundary between the labels, and then we can say based on this boundary, if it's on the right side it's A, and if it's on the left side it's B. So those are two different methods, and as I said here, this is a discrete case classification task, so we're looking for either A or B. But we can also use the same modeling approaches for continuous data sets. So basically, if we look at this data set here, how would you describe this jointly distributed data set as a generative approach if we're looking at the labels as a continuous label? So basically, let's say we're going to do an inference task. We're trying to classify the depth of a certain pixel. Let's say you get a new data point y from the image, and you're trying to you get a new image, the camera takes a new image, and you're trying to find the depth. How would you describe it if we took a sample and we trained our models, and this is what our training data looks like? How would you describe it? So using a generative approach. So if you take 1 second to think about it, and we move on, that's basically how we would do it, right? So we would draw these contour lines, and let's say we get a new data point on y. We follow along the y-axis, and we try to find the most probable location that it'll be and correspond to that to the x value. And we call it continuous, and remember that with a continuous, we're trying to model the joint probability of x and y. So P of x and y, which is proportional to the posterior distribution. And examples of some generative frameworks are Naive-Bayesian Gaussian mixture models. Now let's do the same thing, but describe it as a set of, let's describe it using a discriminative approach. So remember, we're trying to describe the boundaries of this, and given y, what is the x going to look like? So when we do that, it's going to look similar to a regression problem, because regressions are discriminative approaches. So, and as I said, the discriminative approach, we're modeling the posterior directly. So P of x given y, and then we can make a new inference based on that. And some examples of discriminative frameworks, sorry, there's a typo there, is logistic regression, support vector machines, and generalized linear models. So there are some challenges to both approaches. So generative models The true underlying model may be complex, so we really resort to a lot of assumptions and approximations and sampling methods to generate those models. It's very computational heavy, especially because we're spending most of our computing power generating models and not really doing the task of inference itself. And these models are sensitive to assumptions. And those assumptions can really have an effect. So if you don't use any intuition, you're going to have some bad models that don't really describe the data. Discriminative approach is pretty much the inverse of those problems. So we don't know the underlying distributions such as priors. We're not understanding we're not understanding any process that goes behind it. We're just looking for the boundary. And then this means that the discriminant models are also sensitive to bad data and can have a significant effect on the final model itself if we use like mislabeled data and things like that. So let's look back at the Markov random field. How can we describe it as a generative or a discriminative model? So yes, we can describe it as a generative model because we're looking at this term here. So we can describe the prior term, P of x, which is the joint distribution of the configurations, and we could describe that as a Markov random field. But we need to make some assumptions, especially since we're using a generative model. So what can we say about this term here? So this is the problem that people, a lot of research papers look at and try to make assumptions when they're doing the generative approach. So when we use a generative approach, a lot of papers have made the assumption of conditional independence, which basically means given the labels, the observed data is conditionally independent given the labels. And that's basically now we can describe that as a product of the individual sites for so y given the data. And if we take a very common model, Markov random field model, you do that exact that assumption. They call it conditionally independent. And then once you break it down into a Gibbs distribution, we can look at the Clique potentials here. And if we look a little bit closer to the Clique potentials, we see that the Clique potentials depend on the unary Clique depends on the labels of the site and the data of that site. And then the pairwise Clique potentials depend on the labels of the site and then the labels of its neighbors. But when we make that assumption, what do we throw out the influence of neighboring data. So we're not taking into account any pixel values, features, or anything of the sorts of the neighbors. We're only looking at the labels and the data at the site. So this is the major fallback of Markov random fields. So let's talk about this a little bit. So is there an influence of neighboring feature data? So if we look at this building surrounded by nature, and we look at the features of this building, can we say that there's a relationships between the neighboring pixels? And does that affect whether it's going to be nature versus this building, right? So so are we saying that when we say that the term y, the data, is conditionally independent, we're saying that there is no interactions between the two? But it really depends. So if we're doing the task of detecting man-made structures, we can see that the data belonging to such a class is highly dependent on its features. So when we look, there's patterns, there's things like lines, edges, stuff like that. So it's very difficult to say that it's conditionally independent, which a lot of Markov random field approaches may assert. So let's say we want our unary and pairwise clique potentials to incorporate the set of features. So let's say we want our unary clique potentials to be dependent on the entire data set and the label of the site, and we want our pairwise to be all the dependent on the data set as well as the labels at the site and its neighbor. So what would that look like? That would look like this. So we would want the entire data to give some sort of information to our inference problem. So we basically defined a conditional random field when we do that. So let's say, let me give you the definition. So x and y is said to be a conditional random field if when the conditioned on y, the random variable x obeys the Markov property. So now we're looking at the probability distribution of x given y, not just x anymore. And then we can say it's an conditional random field if it follows the same property of Markovinity given its data. And then we can also use the same theorem to describe it as a Gibbs distribution, where we can look further at the clique potentials, which is what we were saying we wanted to find in the first place. Just a quick note, this is a non-sparse conditional random field because we're looking at the entire data set. You can look at just the neighboring data points, pixel values and stuff like that, and that's called a sparse conditional random field. So when I say discriminative random field, I really mean a non-sparse conditional random field on a 2D lattice. So the paper that first implemented this is, they called it a discriminative random field, but there's no difference between that. So what can we say about discriminative random fields in terms of Bayesian inference? And remember that we're saying that it's now P of x given y. Well, what is that? That's pretty much just a posterior distribution. So we can describe this as a discriminative approach since we're modeling the posterior directly. It gives us a method to incorporate spatial interactions between labels and the data. We're no longer relying on approximation methods to generate probability distributions such as the likelihood and marginal. So we're directly describing the posterior. And that makes the parameter learning much easier because you're doing all the training by itself. So that's pretty much a conditional random field. If we discuss discriminative random fields as described by the paper that I discussed, the researchers who developed discriminative random fields leverage the use of domain-specific discriminative classifiers so that they can design their unary and pairwise potentials with arbitrary local discriminative classifiers. So you can use any classifier to describe a discriminative classifier to describe the clique potentials. So here's a little mistake that's x and y. So we can describe the clique potential of site I, unary clique potential as xi and y, and it's equal to the log, and this would be the discriminative classifier term. When we use a discriminative classifier, we can describe the parameters as w, and this really depends on the classifier that you choose. And then si given y is a vector, feature vector that we obtain from our training data. And the same goes for the pairwise clique potential. So we're using a pairwise discriminative classifier, and then the same goes, we use v as the parameters of the pairwise. What can we say about these clique potentials? Well, unary clique potentials is basically how likely a site I will take label xi given image y. And then the pairwise, we can describe this as an adaptive data-dependent smoothing model at discontinuities. So this describes how the neighbors affect the inference. So when we look at Markov random fields, they tend to smoothen noise or consider very sparse labels as noise, since it's just looking at the label set. So if you have 4 pixels, 3 of those pixels are and you're trying to classify grass and dog, and 3 of those pixels are dogs and 1 of them is grass. However, with a Markov random field, the pairwise will usually say, oh, this 1 pixel is just a piece of noise, and it'll consider it a dog. And then it'll smoothen that term, even though it was a grass pixel. But with a conditional random field, it takes the data into consideration. So let's say your model learns that the color green is also affected, so it's probably a grass. So it'll, instead of smoothing it, it'll label it as a grass pixel. So I'm gonna give you a quick example using of like what on a unary clique potential, using a generalized linear model as the discriminator. So the model is described by this equation here, and we're using a logistic link to describe it. W0 and Wi are the weights of the generalized linear model. And then if we describe the classifier, we can take the exponential of the natural log, and then we could describe it like this. And what is this equation? This equation is pretty much a sigmoid function. So now we can say our clique potential is equivalent to log sigmoid given the weights and the vector features. So that's a very simple method for describing a unary clique potential. And then that's the parameters that you want to train. So I'll give a quick overview on parameter learning and inference. So in parameter estimation, there's no assumption of independence of the likelihood term or on the prior, which allows us to model the parameters at the same time. We use standard maximum likelihood approaches to learn the parameters, and it's similar to Markov random field methods because it's in similar forms. The only thing that might be difficult is evaluating the partition function inside of a Gibbs random field, and this might require some generative approaches, so sampling techniques and approximation. So this can be quite difficult. And then the inference task, we're basically just trying to find the optimal configuration of x in P of x given y with respect to some cost function. And some methods include finding the maximum a posteriori. So you're looking for map using a 0-1 cost function. So the researchers in this paper didn't find any great results using it. There's also maximum posterior marginalization method, as well as looking at local map estimations using iterative conditional modes, and simulated annealing. So I won't go into depth in these because they are all research papers on their own, but these are just some properties of parameter learning and inference. So when we look at the results, what we see when we're comparing it to Markov random fields, we see so main thing is we see increased detection rates. More things are considered. Oh, so the task is man-made structure detection. We see many more actual. So here you see that it's not being labeled, whereas it's actually being labeled. And we're seeing significant reduction in false positives. So here you see like the tree is being detected as a building and stuff like that. So this is what I wanted to describe earlier. So let's say you have image where it's mostly grass and you have some building here. So in a Markov random field, because most of it is considered grass, the, the labeling often smoothens it out and considers a lot of things noise because it's surrounded by mostly grass pixels. So it tends to overestimate grass and underestimate the building. And then here you could see that it's detecting some noise even though it's not. And then in the using a discriminative random field or a conditional random field, it's taking into account the features of the building as well. So you have a better detection rate than in same here. So you're looking at the building, but it's next to some trees and maybe it's misdetecting the maybe some properties because it's close to the building as the building itself, whereas the discriminative random field looks at the entire picture of the features. And again here, same thing, so it's mostly background and then some buildings, and the Markov random field approach doesn't classify a lot of it. It's not looking at data features like some squares and stuff like that. It's not taking that into account. It's just saying, oh, this is mostly background and there's just some building. Whereas here, it's saying, okay, it might be the same color, but there are some pixels that follow some pattern that describe a building. So here it has much better detection rates. So thank you very much for listening to the presentation. That's pretty much it, and I hope you learned a little bit more about conditional random fields. Thank you.